Today we're going to talk about modeling direct variation and how to do so. We'll note that what's nice about this situation here, this equation of modeling direct variation, is nothing different from what we saw yesterday in terms of slope intercepts. Just it's to be more or less a special case of it. A direct variation equation is a linear equation that contains the origin. Hopefully you recall the origin is the point 0, 0. So what that boils down to is it's a line. And if here's our axis, then it's a line that goes through 0, 0. Or maybe it's more of this like less steep and negative version. These are all direct variation. Lines that could model direct variation. So this means that the y-intercept is 0. And therefore it has a special equation. The equation is always in this form. Y equals a times x, where a is the constant of variation. What's constant of variation? It's basically the slope of a direct variation equation, generally referred to as A. The reason I'm going to refer to as A and not M. Note that this could just be MX. I'm referring to it as A because your book uses that terminology, so I want to make sure that you feel confident about that terminology as well. So if I want to tell whether an equation represents direct variation, I know that because it's going to be a line that has the y-intercept, or the value of b from slope-intercept form is 0. So if I write my equation in slope-intercept form, and it happens to be this form, where there's no constant, where the y-intercept is 0, then I know I'm in direct variation. So for example, in this first guy here, let's try to get this in slope-intercept form. So I'm going to try to solve for y. And I do so using my normal algebra rules. And I get an equation that looks something like this. Yes, this is direct variation. The y-intercept is 0. There's nothing there. That's good. So since it is, then we'll identify the constant of variation. Well, the constant of variation is the slope of this line. So maybe I'll try again here. So here's another equation. Let's try to solve for y. We'll just try a little pro trick here, and I'm going to add y to both sides. I get 2x equals y plus 3. Let's subtract 3. And I'll get 2x minus 3 is y. You could flip this if you really need to. Is this direct variation? Notice that the y-intercept, or b in this case, is negative 3. So no, because b is not 0. So kind of two big examples. I know right off the bat it's not direct variation because there's something other than 0 as the y-intercept. So Can't be direct variation. Okay, try the same thing here. Y equals x plus 1. No. B equals 1. Again, there's a y-intercept, so it can't be direct variation. Yes, this is direct variation. So y-intercept is 0. Constant of variation is -2. So in this first section, we identified whether or not these could be direct variation by their definition. Graphing direct variation equations is pretty nice. They graph identical to how we did yesterday, meaning we'll still find the y-intercept. In this case, the y-intercept is always 0 since it's direct variation. And I'll still use slope, or the constant of variation, to help me graph my line. So I know that slope is change in y over change in x. So I'm going to go up 2, and I'm going to go to the right 5. 1, 2, 3, 4. I kind of have to go off paper a little bit. Voila. Okay, kind of same game. Y-intercept is 0 since it's direct variation. This constant of variation here is kind of written oddly. So I claim that this is the same as this, which is the same as this. So if there's a negative in front, I can give the negative either the top or the bottom, but not both. This helps because this tells me, say in this first case here, maybe my slope, my change in y says to go down 1, my change in x says to go up 2. So maybe I go down 1, and to the right 2. This would be slope of -1 over 2. Well, instead we use slope of the second one. So y goes up 1, but x goes -2, goes right in the previous one. So I go up 1 and to the left 2. And notice those points still form a straight line. So draw my line. There we go. There's my line corresponding to this constant of variation. So what can we see? Well, maybe there's some applications to this. So how about just a mathy one, where I tell you that graph this direct variation that goes through 2 points. So I don't tell you what the equation is, but I tell you the points on it. And the key here is I know that it's direct variation, which means that the formula for all direct variation equations is something like this, which means I just need to figure out what A has to be. So I'll pick any point that's not the origin, I'll plug that in for x and y. So for example, I'll plug in 3 for y. I don't know what A is. I know x is 2. So I'm going to use that to figure out what A has to be. So let's get A by itself. A is 3 halves. Which means in turn, now to write my equation, I'm going to take that number and plug it back in there. My final equation of my direct variation situation here, y equals 3 over 2 times x. So I'll graph this. I know it goes through 0, 0, and 1, 2, 1, 2, 3. My line looks something like this. Now I need to answer, I'm asking this, find the value of y when x equals 14. Well, this is handy because I have an equation. I should be able to plug x into it, figure out y. So if y is 3 halves times x, that implies that y is equal to 3 halves times 14. What's y? Well, that's 42 halves. Y is 21. So when x is 14, y must be 21. This is a very important example. This is a sort of thing that's going to, say, show up on a quiz at a later time. Those of you currently enrolled. So let's think about this situation. So we have an object that weighs 100 pounds on Earth and would weigh just 6 pounds on Pluto. I'm going to assume that the weight of P on Pluto varies directly with its weight E on Earth. First, I need to write a direct variation equation that relates P and E. Again, since P varies directly with E, varies directly means that P is equal to something times E. Just like we did before with X and Y, we can do the same thing with whatever variables we want, since I know they vary directly. Well, can we figure out something that corresponds here? Well, I think we have a pretty good one, in that we know that if you weigh 6 pounds on Pluto, then you weigh E pounds, or 100 pounds on Earth, This constant of variation you get by dividing, or A in this case is 6 over 100, which simplifies to 3 over 25. Therefore, my equation, once I know my fraction here, weight on Pluto is equal to 25ths, times my weight on Earth. Be my equation. How is this useful? Well, that's pretty nice, because what would a boulder weighing 750 pounds on Earth weigh on Pluto? Well, I have a function for that. I know I'm trying to find its weight on Pluto. I know that my weight on Earth I get by taking 3 over 25 times its weight on Earth. Weight on Earth is 750, not 75. And therefore, if I multiply 3 over 25 times 750, I end up with a weight on Pluto of 45 pounds. Again, in 2 parts. Write an equation, and then use the equation to come up with a further value. One last example. This table shows the cost of buying used DVDs at a music store. First of all, explain why C varies directly with D. If it varies directly, it better be linear. So the change better be the same. So I better figure that the change in DVDs gives me a consistent change as we go through. And I think if we use a calculator, we can see that these changes are the same. We'll calculate what that is. 51. My rate of change is the same. Moreover, why does C vary directly? What's it mean to vary directly? Varying directly means that the y-intercept is 0. Namely, if I sell if I buy 0 DVDs, then how much should it cost me? Well, it should cost me $0. I think for this situation, it makes sense. So if you buy 0 DVDs, it costs you 0 money. And also the price stays the same. So it costs me the same amount for every CD or DVD in this case that I buy. Write my direct variation. Well, I need to know how they relate. One way you could do so, again, since the cost varies directly with the number of DVDs sold, you could pick a pair here and plug it in and say, let's say 2577 is equal to my constant variation times 3. A is therefore 2577 over 3. A is 859. So again, take A, plug it in here, and my equation is the cost is equal to 859 times D. And that's